In this series of videos, I'm attempting to offer advice to anyone who wants to get started in electronics. Of course, I can't cover every aspect of electronics in one or two videos, so I won't be going into how a transistor works or how a MOSFET works in this video. But if that's the sort of thing you want me to look into, if you have anything in particular you want me to cover, then please leave a comment and I will try to include it in a future video. In this video, what we're going to do is look at, it's a follow-on from the previous video in this series where I demonstrated a switching supply and compared it against a linear supply. And in that video I didn't really go into too much detail as to how the switching supply worked. I did leave a link to a previous video that explained how it worked in some detail. But really it was just a comparison between the two general types of supply. I did say that it would be an interesting experiment to try and play with this and improve its efficiency. And I had quite a few questions on this, and several of the questions were about how to go about actually improving the efficiency of this. So that's what we're going to look at in this video. So just to recap, the circuit we're looking at is this one. It's very simple, just a simple switching circuit. We have a pass device, which at the moment is a 2N3055 bipolar transistor, and it's just switching on and off using a pulse width signal. And the way this works in brief, when this pass device is on, current starts to flow and build up in the inductor, flows through into the output capacitor, and the load is of course across here. It then turns off and the inductor takes over, sourcing the current through this loop using this diode, and then it switches back and forth and it alternates between current being supplied from the source or current being sourced from the inductor. Everything to the left of the power device is really just a driver for the pass transistor. Normally what you would do is have a feedback system, and often you derive the oscillation for this circuit from the ramping up and ramping down on the output, and you use that to control the pulse width of the pass device. In this case, to make it more consistent and easier to explain, I'm actually driving this from the one of the bench signal generators, and I've got it set to 45 kilohertz, and it's generating a pulse width controlled signal, and I will adjust the pulse width whenever we make any changes to try and keep the output voltage as close as I can to 5 volts. What we're really looking at here is the efficiency of the circuit. That's how much of the power it's using is actually made available at the output, and we'll see how we can go about improving this. The best I could get before was around 78.1%. So we'll just recap and we'll measure the efficiency, or just calculate the efficiency now from this starting point. So on the O1 supply it shows the output power, but what you can do if you can't read that is just multiply these two numbers together and that will give you the output power. And on the Kunkin electronic load, it shows the output power on the bottom line. Apologies for any flicker on the Kunkin. I've got the Kunkin set to a constant resistance mode 10 ohms. I'm going to leave this set the same all the way through this video. The O1 supply is set to 10 volts with a 3 amp current limit, and again I will leave that set the same all the way through this video. On the scope, the blue trace is the signal coming from our signal generator, so that's what's driving our circuit, and the yellow trace we'll use for various inspection of what's going on with the circuit. So we'll start by calculating the efficiency. So we divide 2.52 by, and the O1 showing 3.28, and that gives us an efficiency of 76.8%. so I'll make a note of that. So 76.8%. So that is our current efficiency. That's what we want to try and improve. So there's various ways we can start looking at how to improve this. Changing the circuit layout is the first one to look at. So if if we just take a very simple example, we've got this 10,000 microfarad capacitor, which is this one, and we've got another capacitor here which is across the input, it's across our 10 volts power rail. We can start with something extremely simple and just move that closer to our switching device. And now adjust the output, it's risen slightly. It's now back down to roughly what it was. If we now recalculate the efficiency, so that's now showing us 2.51 divided by, we're now getting 3.25 on the O1 supply. And that's giving us 77.2%. So I'll write that down. Okay, so we've gone from 76.8% to 77.2% just by moving the capacitor, the source capacitor, closer to our switching device. We'll move it back. Okay, and we'll recalculate using the values currently displayed. So it's 2.5 divided by 3.25, and that's now 76.9%. So again, it's dropped down fairly close to what we started with, so it is repeatable. Just moving the capacitor closer to the pass device improved our efficiency by about 0.4%. We gained about 0.4%, which is actually quite good. I'm going to leave it where it is for now to keep it out of the way, but just bear in mind that the layout of the circuit, especially in something that's switching, makes a big difference, and that can become more of a dramatic effect as the switching currents rise. The next thing we can do is start looking at the components we're using. So I'm going through this very quickly. You can do all manner of experiments with this, try various things, various different devices. But you want to be looking at what you believe may be causing the inefficiencies. The inductor's a big one, but I'm going to leave that as it is for this video. This is something that is probably a video in its own right in terms of how to go about designing an inductor for something like this. But I'm going to leave it as it is so we get consistent results. If we start changing this, it will be very confusing trying to figure out how the efficiency is changing, because it will affect everything else. But what we can do is look at the pass device. Now, one of the issues we get with a supply like this, and one of the reasons it's not very efficient, if we grab the data sheet for the 2N3055 and we start looking through this, then the bit we're interested in is the saturated voltage, the on voltage drop across the device when the device is saturated. We are intentionally driving this into saturation, so what is the voltage drop across it going to be when it's fully switched on? So if we look at the spec sheet and we find the collector emitter saturation voltage, we can see that it's anything between about 1 volt and 3 volts depending on the current that the device is passing. If you notice in the previous video, as the current started to rise, the efficiency got rapidly worse and worse. And that's largely because of this effect where the current that the device is passing increases as the load increases, and so the voltage drop across it rises accordingly. And 3 volts is quite a significant voltage drop, especially, we've got a 10 volt supply here, so that's nearly a third of the supply gone. It also accounts and explains why the device heats up, because it's got 3 volts across it and the current flowing through it, of course. Now it is switching, so it's not on constantly as it would be in a linear supply. We've got what is approximately a 50% duty cycle at the moment, so although we've only got half an amp on the output, we could estimate and say it's pulsing at around 1 amp. And looking at the spec sheet again, then we can see that at 1 amp we'll be getting something a little over 1 volt. We can actually measure that if we get the scope and we look at the supply. So I'll connect it to the supply rail, And what we'll do now is we'll set the cursors on, and I'll set one cursor to the supply, so the top cursor is now set to the supply voltage. And what we can now do is move the scope to the output of the pass device. So looking at the schematic, then the first cursor, the top cursor, is at this point, and we're now monitoring this point. And we can see we've got this square wave showing. That's the switched output of the pass device. And so what we'll now do is move the cursor to that point, and the delta value, that's the difference between the two cursors, is now showing up at 960 millivolts, so about a volt, which is what we expected. So that means we have 1 volt being dropped across this device with this load. Now if we were to increase the load and get up to 4 or 5 amps, then we'd be dropping 3 volts or more across this device, which obviously makes it very inefficient, and that's where the bulk of the inefficiency lies in this design. So what we can do to try and combat that is find a more efficient pass device. So if we can find a bipolar transistor with a saturated voltage that's less than a 2N3055, then it should improve our efficiency. And I just happen to have something like that. So we've got this. So this is a 2N5302, and the collector emitter voltage drop when it's saturated is about 1.5 to 2 volts. It's about half what the 2N3055 would give us. Okay, so I'm going to swap this out, and then we'll do a comparison and calculate the new efficiency. Okay, we've got our new pass device. We'll switch the power back on. Notice that the output voltage has risen quite significantly, which is a good sign. It probably means the supply is now more efficient. So I'll adjust the pulse width to bring us back down close to 5 volts. And we'll calculate our new efficiency. So 2.48, which is what the electronic load is showing us, divided by 3.119, which is what's showing on the O1, and we're now getting 79.5%, so I'll write that down. Okay, so we went from 76.8% to 77.2 by moving the capacitor. The capacitor's back where it was, so we're really at this point in terms of the layout, but by changing the pass device to a device with a lower saturated collector emitter voltage, then we've raised the efficiency now to 79.5%. In other words, we've gained the best part of 3% in terms of the efficiency of the supply, which is a significant change. Now you can keep doing this, you can keep modifying the design, the layout, optimizing components, but really you're never going to get much over 80% with a bipolar transistor in a circuit like this. You can improve the switching efficiency, you can put snubber networks in, you can optimize your inductor, everything else, but because the forward voltage drop is always going to be relatively high, there's not much you can do to combat that, and so the best option to improve the efficiency of a supply like this is to get rid of the bipolar transistor completely. And that's what we're going to do now. I'm going to get rid of the bipolar transistor, and we'll use a power MOSFET instead, and we'll see if that improves our efficiency at all. So I'll get this swapped out. I'll have to rearrange the circuit a little bit, but all I'm really going to be doing here is removing this pass device, get rid of all the drivers, and then we will put a power MOSFET in this position. Okay, I've put an IRF 4905 in place of the 2N3055. It's a fairly modern power MOSFET. It's not particularly optimized for this sort of operation, but neither is the 2N3055, so it's kind of a good comparison to use. And what we can do now is turn the power on. Notice that the blue trace is still the same, and what's changed is the way the switching works. So I will need to now adjust the output voltage. It's gone up to nearly 8 volts, so I'm going to change the pulse width. You'll see the pulse width changing as I adjust it. I'm going to bring the voltage back down to around 5 volts at the output of the switching supply. Okay, so that's now giving us around 5 volts out. I haven't changed anything else apart from the pass device and the way it's driven. The inductor, the diode, the capacitors, the way the circuit output is laid out is identical, but we'll work out the efficiency now. So 2.48 divided by, and the other one is now showing 2.929, and that's giving us 84.6%. So we'll make a note of that. Okay, so we're now getting 84.6%, and the starting point was 76.8. So we've gained almost 8% in terms of the efficiency of the supply by doing nothing more than swapping out the type of pass device. And what we can start doing now, because the MOSFET is more efficient at switching, and this is one of the issues with bipolar transistors. They're current controlled devices, which means we needed quite a lot of current flowing through the driver transistor, which is why we have a 12 ohm resistor here. Now that of course means that this device itself will pass quite a lot of current. Now most of it's going through to the load anyway, so it's not all wasted, but this will be dissipating power as well, so it's quite inefficient. You need quite complex drivers to drive something like a high power bipolar stage, and that absorbs energy, makes the efficiency drop still further, and that becomes worse because you're losing energy each time you switch. The faster the switching rate, the more energy you lose on average, so it becomes inefficient to switch at high speed. Now we've got the switching far more efficient, what we can do is actually increase the switching frequencies. So I'm going to turn the frequency up from 45 to 55 kilohertz. Now of course the output voltage has risen, so we'll change the pulse width to get it back down to an output of 5 volts. We can now recalculate the efficiency. And we're getting 84.9%. So that's now gone up by 0.3%. We were getting 84.6, now getting 84.9, and you could now play about with various settings. So by making small changes, we can improve the efficiency of the supply in small increments. We'll move the capacitor across now and see if we get a similar gain to the gain that we got when we did it with the bipolar. The output voltage has risen. Recalculate the efficiency. And notice we're now getting 85.3%, so it's gone up by nearly an entire percent by adjusting the frequency and moving the capacitor closer to the load device. So we're now at well over 85% from our starting point of 76.8%, so we're well on the way to gaining 10% efficiency in something that was already reasonably efficient. And if you tinker with this, you'll probably be able to get it up somewhere 88-89% efficient, even on a breadboard like this. So a lot of fun to play with this, change pretty much everything, mess about with it, try different devices. As I said, this video is only really intended to try and encourage experimentation. There's an awful lot you could do to improve the efficiency here. This has just been cobbled together with values I pulled out of the air, but you could look into each of the various aspects of this in a lot of detail and figure out how to make it switch more efficiently. So you need the pass device to turn on and off efficiently. I would also say that one of the reasons we've gained with the power MOSFET, of course, is that instead of having anything up to 3 volts across it when it's fully saturated and a high current flowing through it, this device has a non-resistance of 0.04 ohms. So even if we're passing an average current of around 10 amps, we're still only passing about 1/7, or dropping rather about 1/7 of the voltage that we would be with our bipolar device. So needless to say, despite being a smaller package, this is completely cold. It's not warming up at all. And this is a final experiment for this video. I'm going to increase the current and see if the device can survive at 2.5 amps. If you remember, the bipolar transistor started getting fairly hot, although it is a much bigger package, of course. But let's see if our power MOSFET can survive. Okay, I've got the thermal camera on standby. Currently the device is about 25 degrees centigrade, and I'm going to change the Kunkin supply. I'm going to set the resistance to 2 ohms, which is what we had when we're testing high current with the previous video. I'll now turn the supply back on, and we'll keep an eye on the temperature of the pass device. I need to adjust the output back up to 5 volts, of course. Which is there. So now we'll have a look at the pass device. It's 34 degrees. So it is heating up, but not particularly quickly. Do a quick calculation of efficiency at this power. So we're getting 12.28 watts at the output, and the O1 supply is showing 17.81, and that's giving us around 69%, so much better than we were getting with this power level with the bipolar. It is getting hot, so we're now up nearly 60 degrees. But it is passing 2.5 amps, and there is no heatsink on it at all. So as you can see, it's a very good way of designing a supply like this to use a power MOSFET in place of a bipolar transistor. The output will be far more stable, the efficiency of the design will be much higher, and as I said in the previous video, this sort of circuit is a lot of fun to play with, and it's a really good way of learning electronics. If there's any aspects of electronics you want me to cover, if there's any particular devices you want me to have a look at, then please leave a comment. But the idea of this series of videos is to slowly build as we go along on the various different elements within electronics, and always really focusing on the basics, not because they are simple, but actually because they are the things that are harder to learn. Very easy to learn to play with an embedded microcontroller board. You just follow the instructions, but going this route will enable you to design your own microcontroller systems. So a lot of fun. This is what I'd really recommend if you're getting into electronics, and as I said, the amount of fun you can have with something like this is almost endless. There's the permutations, the variability, the different experiments you can carry out are pretty much endless.